Nanotechnology is also an information technology. It is utilizing information processes to control and reorganize and re-engineer matter and energy at the molecular level to create new materials. That's the frontier we're on right now, but ultimately new devices that are actually nano-engineered. There's a whole emerging industry of three-dimensional printers. That's not nanotechnology today. The scale is about at the micrometer level. But ultimately, we're, as I mentioned, reducing this feature size at a scale of 100 in 3D volume per decade. We'll be down to the nanoscale in the 2020s, and we'll be able to actually print out a very complex three-dimensional objects at the nanoscale. It's basically at the level of molecules. That will be the long-heralded desktop factory that Eric Drexler first started talking about a quarter of a century ago. And this progression, this reduction of size, this increase in the price performance, scale, and bandwidth of information technology, the reduction of the size of technology in general, is a very predictable phenomena. It really belies the common wisdom that you can't predict the future. It's really remarkable just how predictable this phenomena is. And I'll show you quickly just a few examples of this to show you the pervasiveness and the predictability of this exponential growth. It's not an approximation when I say that, for example, the Genome Project doubled in scale every year. The total amount of genetic data we sequence doubled every year. The cost came down by half. It's not an approximation. It wasn't 50% one year and 200% the next year and averaged out sort of roughly to 100% each year. It was exactly a doubling every year. And so skeptics dismissed the project halfway through the project. This is typical. People dismiss these exponential progressions when they're solving 1% of a problem. I predicted a World Wide Web connecting hundreds of millions of people to each other and to vast knowledge resources emerging in the mid to late 1990s. I made that prediction in the early 80s. People dismissed the ARPANET because it was a very small-scale phenomenon. The entire defense budget could only tie together a few thousand scientists. But that's the power of exponential growth. It happened right on schedule. And the Genome Project was dismissed halfway through the project because skeptics said you're halfway through the timeline and you've only sequenced 1% of the genome. That's typical for an exponential progression. You start out doubling little numbers. It looks like nothing is happening. But by the time you get to 1%, now you're ready for some real traction. It continued to double every year. 1% is only 7 doublings away from 100%, and the Genome Project was finished 7 years later, a year ahead of schedule. We see the same phenomenon now with solar energy. People dismiss it. Oh, it's only 0.5% of the world's energy needs. It's just a fringe player. It's nice, useful, but it'll never be significant. It's doubling every 2 years because of nanotechnology, because we're applying nanoscale processes to new solar panels and energy storage devices. As a result, the costs are coming down dramatically, and the total amount of solar energy is doubling not every year, every 2 years. But it didn't start 2 years ago. It started 20 years ago. It's already doubled 10 times, and it's now 0.5%. It's only 8 doublings away from meeting 100% of our energy needs. And I had this conversation with the Prime Minister of Israel recently at the Israeli Presidential Conference, and he said, well, do we actually have enough sunlight to do that with? And I said, actually, we have 10,000 times more than we need. We only have to capture 1 part in 10,000 of the sunlight that falls on the earth to meet all of our energy needs. And we will do that at very low cost within 16 years. So the next year, he made an announcement, which he based on our conversation, setting a 10-year goal to completely replace fossil fuels with solar energy and other renewables using Israel's best scientific leadership. And I told him afterward, I said 16 years, not 10 years, but he's being a little optimistic. But many people feel this will never happen or will take centuries because our intuition is linear, not exponential. We think in a linear way. That's actually hardwired in our brains. But the reality of information technology is exponential growth. And it's very unintuitive, but it makes a huge difference. As I mentioned, 30 steps linearly is 30 steps exponentially is 1 billion, and it makes a fantastic difference. And that's why my own predictions have been daunting to people, but I have enough of a track record, having started this 30 years ago, that many of these predictions are about the past now and have come true. And when they come to measuring these key issues of the basic fundamental measures of information technology, the size of various technologies, like the size of the key feature size of semiconductors, or the number of MIPS per dollar and bits being moved around on the internet, those kinds of predictions have been very accurate because these are very smooth and predictable trajectories. And the final frontier of biology and health and medicine is really to re-engineer completely this very complex system. Now, biology is remarkable. It's very intricate. It's very clever. But it's full of downsides, as we've all noticed. We all have to spend a lot of time maintaining our bodies, and that's when things go well. And it's subject to a lot of disastrous scenarios. And ultimately, we are going to reverse engineer biology, and then re-engineer it. And there isn't a single organ you can talk about where there aren't already extensive projects to re-engineer, either to augment or to replace those systems, from the heart and artificial pancreases, artificial kidneys, portions of the brain. That's not just futuristic. There's an FDA-approved neural implant that replaces the biological neurons destroyed by Parkinson's disease. It's not blood cell size today, so we can't send it in non-invasively through the bloodstream, which we will do in 20 years. It's pea size, pretty small, but does require surgery. Already now, for 2 generations, we can download new software to the computer inside your brain if you're a Parkinson's patient. The latest generation, the software is actually quite complex, and there was a recent New York Times article expressing concern that people would hack into the complex software that people are downloading into their brains wirelessly. So that's today. If you go out 20 years, these devices really will be blood cell size. They won't just be experimental. These won't be just animal experiments. We will be augmenting and replacing biological functions with nano-engineered systems that go far beyond the capabilities of biology. As I've mentioned before, the respirocytes designed by Ron Friedis are about 1,000 times more capable in storing and releasing oxygen and carbon dioxide than our biological red blood cells. And if you replace a portion of your red blood cells with these devices, you could do an Olympic sprint for 15 minutes without taking a breath, or sit at the bottom of your pool for 4 hours. So these are the kinds of capabilities that we will be enhancing normal biology with by merging with non-biological systems through nanotechnology. So let me show you quickly just how pervasive and predictable a phenomena this is. In the case of computation, it goes back to the 1890 census, and then we'll talk a little bit more about some of the implications.